Okay, so welcome to our course R24 manufacturing process. We already started a metal joining process, right? So as of now, we discussed the introduction part and the types of welding, and we discussed some of the welding process, right? So this is our content. So we begin with our introduction. So it's a material joining process which produces coalescence of materials by heating them to suitable temperature with or without the applications of pressure, or by the application of pressure alone, and with or without the use of filler metal. So I hope you know the filler metal, right? The filler metal, it's a material. It is used to fill the metal, right? So if you want to join two parent metal, the in between the gap between these two metals are filled with the filler metal. Some application we use filler metal, some welding process we never use filler metal. The parent metal itself, it converts as a molten state, and we apply some pressure, and it will allow to solidify, and we will get the final product. This is the introduction part. So I hope we know that welding is the permanent joint. So these are the classification we have. This is a sub classification. So there are main 7 category: gas, arc welding, resistance, thermite, solid state, newer welding, and filter process. So in this video we are going to see the two things. One is solid state welding, and then newer welding, right? So we are going to see one by one, right? So first of all, what is meant by solid state welding, right? So the group of welding process wherein coalescence is produced at temperature essentially below the melting point of the base metal being joined without the addition of filler metal. Pressure is always applied, right? So solid state welding, it means it is a group of welding process, right? So it is a group of welding process wherein coalescence is produced at temperature essentially below the melting point of base metal, right? So assume that if I am going to join two metals, it may be the aluminum. The melting temperature is, assume that it is 100. Assume that it is 100. Then we will make a temperature. We will increase the temperature of base metal below 100. It won't reach 100, right? So because 100 is a melting point. So below melting point, we increase the temperature and we apply the force, right? So from applying the force, it will join, right? So we never add any filler metal, right? So this is what a solid state welding, right? So there are many types. One is a friction, ultrasonic, diffusion, explosive, and then forge welding, right? So we will see one by one, right? The first one is friction welding, right? So we know that friction means if the two parts are collide, or if the two parts are met, definitely the friction will create. So normally all machining process friction will occur. This friction may generate the heat. So in machining also, the heat generation is not, we can't avoid that heat generation. In order to avoid, or in order to reduce the heat generation, we use some cutting fluids like lubricants, right? So but here we are going to make a joint with the help of friction, right? So we are going to make a friction, right? So the friction will generate the temperature. That temperature is used to make a joint. So in this welding process, the fusion is produced by rotating one of the weld parts to be joined against the fixed surface of the other part. So just assume if it is a lathe machine, we have a headstock and then tailstock. So your object is placed in the headstock, and the another object is placed in the tailstock. So we have a two object 1, object 2. Object 1 is placed in headstock, object 2 is placed on the tailstock. Now you start your machine tool, right? Engine, lathe. So it will rotate. So headstock will rotate. So the workpiece 1 rotates, and we will move, right? We will move tailstock, and the object 1 and 2 will touch us, right? So definitely the friction will occur. That friction will generate the temperature. That temperature is used to join these two metals, right? This is what a friction welding. So the two metals are joined with the help of friction heat, right? So large amount of pressure will be applied at the end to complete the joint. Pressure and the rotations are maintained until the resulting high temperature makes the component plastic, right? The plastic means permanent joint, right? So this is what a friction welding. The advantages are, it is possible to weld the following combinations such as copper to carbon steels, copper to aluminum, aluminum and its alloys, brass to bronze, tool steel, stainless steel, and aluminum and tungsten, etc. So one of the advantages in solid state welding is you can join two dissimilar metals, right? So previous cases, for example, previous other welding process, if the parent metal one, if it is aluminum means, then parent metal 2 should be the aluminum. Then only we can make the joint. At the same, if you use filler metal, then that filler metal also same as to parent metal. This is the combination. So this is the main constraint or limitations. But solid state welding, we can join two dissimilar metals, right? So this is one of the advantages. Two dissimilar metals. Even you can you can join the mild steel with the aluminum. You can join the carbon steel with the HSS, right? So any combination you can join. This is one of the advantages for friction welding. So it requires less time operation. Changing of granular structure is less because the heat is generated at the end or at the edge of the workpieces. So it won't affect the other part of the machine shop. So edge மட்டும் தான் heat ஆகும். So that granular structures the change பாத்தீங்க அப்படின்னா it's very less. The weld joint may have not be heat treated again. So no need to heat treatment again or other secondary process, it's not required. It has no need for flux, filler, it is free from smoke, spatter and slag. And it is a simplicity of operations, right? So these are some of the advantages, right? The next one is limitations. The process has been applied only to small bar stocks, right? So it is one of the limitations. Sometimes heavy flaws may have to be removed. Thrust pressure in the range of 700 to 2800 kg per centimeter square may be the required, hence heavy rigid vessel is required, right? So friction, we are moving the part 2 or object 2 against the rotating part of object 1. So we need to apply more pressure, more thrust to pressure. This is one of the limitations. So if you apply more pressure, that vibration may happen. That vibration should adapted with the machine itself. So we need a heavy rigid machines, right? So the applications are drill, tap, reamers, etc. Joining with shank, right? And to join steering shaft and warm gear, engine valves, power transmission shaft, etc. So production of biometallic shaft joining. These are some of the applications for friction welding. So friction welding is nothing but we are going to join. We are going to make a joint between two dissimilar metal with the help of friction heat or friction temperature, right? The second one is ultrasonic welding. So this is also one of the solid state welding process where joints is produced by the local application of high frequency vibratory energy to the workpiece, which are held together under pressures, right? So previous case, the two pieces are joined with the help of pressure heat, but this case, the ultrasonic, the two pieces are joined with the help of vibrations, right? So vibrations. If the two objects are vibrated, then the friction will occur, and similarly the temperature will increases. So with the help of this temperature, we can join the two metal. So it is a solid state welding process where joint is produced by the local application of high frequency vibratory energy to the workpiece, which are held together under pressure. The average frequency used in ultrasonic welding is 20 kHz and the lower cases 10 kHz. So it will be the range of 10 to 20, right? So kilohertz, the average range. But some special circumstance we use up to 170 kHz, right? So this is what one of the applications. But if you want to utilize 170 kHz, you need to have a rigid structures, right? You need to have a rigid structures. These are some of the applications for ultrasonic. This is ultrasonic welding. So from this image, you can easily observe that we have a transducer. So transducer is a device which converts one form of energy into other form of energy, and we have a coupler and we have a sonotrode tip. So generally we say electrode, but here we say it's a sonotrode because here electrode means generally we have a two parallel electrodes, but here we have only one. So generally we say it's a sonotrode tip, and the sonotrode tips are connected with the coupler, and we have an anvil or base, right, table, and we place two objects, and the top of the objects we placed our sonotrode tip. If you supply electric current, the transducer converts electrical energy into vibratory energy. That vibration will carried out by sonotrode tip. The sonotrode tip gets vibration. So due to the vibration, the temperatures will rise, right? So this temperature used to join these two pieces. This is the working principles of ultrasonic welding, right? So the operations of ultrasonic welding, the workpiece are clamped between the sonotrode tip and anvil. A transducer attachment converts the electrical frequency into ultrasonic high frequency energy. So this is the applications. So transducer is a device which converts one form of energy into other form of energy. Generally transducer, here the transducer converts electrical form of energy, electric form of energy is converted to vibration of sonotone tip. The high frequency energy is transmitted to the weld joint through the weld tip. The tip oscillates on the weld joint. The combined effect of pressure and the high vibration causes movement of the metal molluscs to bring sound joint. So this is what ultrasonic welding. The metallic bonding is carried out in solid state without applying the heat or filler rod. So this is the working principle of ultrasonic welding. So we have advantages, limitations, and applications. So advantages are we don't need any filler rod or flux. We no need to prepare any surface treatment, right? So other welding process we need to prepare surface. So before joining we need to prepare the surface. If any dust particles or dirt particles are present or any foil particles are present in the workpiece material, we need to remove, or we need to do some primary process, right? So in order to prepare surface treatment. But here there is no need for surface preparation. You can get good surface finish, very thin material can be welded, metals can be having different melting temperatures, can be welded without any hazards, right? This is what dissimilar metals, we can weld dissimilar metals. But we have some limitations, so uneconomical and restricted to thin materials, right? So assume that we are going to make a joint with the help of vibration, so it is not unethical, uneconomical, because we need to generate more frequency. So if you want to generate high frequency, then you need a more costly machine. So this is what uneconomical and restricted in thin metals, right? So thin metals it is restricted, and materials being welded may stick to anvil or tip. So this is another one disadvantages. Even though the two metals are joined, if the metal may be stick to the anvil or sonotone tip. This is one of the limitations. Applications of ultrasonic weldings are: it is best suited for thin cross-sectional metals, welding of electrical and electronic components, welding sheet and wire of aluminium, nuclear fuel component welding. These are the applications of ultrasonic welding. Now I go with the next topic called diffusion welding. Right, so diffusion means generally we apply more pressure on both the sides of material, both the sides of workpiece. So the diffusion means exchange of atoms will happen. If you apply more pressure, then the temperature will increases. That due to the temperature rise, the atoms or the molecular of two metals may be transfers. The energy transfers. It will make a bond. This is what diffusion welding. So the diffusion welding is one kind of solid state welding process. The weld joint is produced by applying a tremendous pressure on the job. The matched metal surface should be perfectly clean and mated so that actually grow together by atomic fusion. But here we need a surface treatment, right? So before weld we need to prepare the surface. So this is a very simple process. Diffusion welding means if I have a two metal, right? So I'm going to join. So I'm applying more pressure on both the sides of metal. So if I'm applying the pressure, definitely the temperature will increases. So that this temperature is used to change the atoms, right? So exchange of atoms will happen. This will make the bond or joining. This is what a diffusion welding. Right, so the diffusion welding process, any surface can be welded except dead smooth surface. Every metals have a peak and valley points, right? So dead smooth surface means if the two metals are good surface finish, mirror finish, then you cannot find any peak in the surface. Generally diffusion welding requires peak, right? So the surface we need some peak. 1 minute. Right, so diffusion welding process, one of the limitation is we can't perform diffusion welding in dead smooth surfaces. So dead smooth surfaces means the surface, if it is a good surface finished, means we cannot weld with the help of diffusion, because diffusion welding needs some kind of peak in surface, right? So initially the faces to be welded are made together and held under huge pressure. So we apply more pressure up to 400 to 700 kg per centimeter square, such that the roughness of metals are deformed. The weld metal surfaces are diffused under pressure. So after loading for a certain period of the entire area of contact surface is bonded. So this is what a diffusion welding, right? So we have a metal or ceramic. So this is also used for dissimilar metals. So we have some peak. So if you apply pressure on that, the peak will reduce. The atoms between these ceramics as well as metals get exchanged. So we can get this bond like this, right? So this is what diffusion welding, right? So the stages are represented here, right? So generally materials are zirconium alloys, titanium alloys, nickel based alloys. These are the metal alloys we can use for diffusion welding. Advantages are, due to cold welding process, the base metals chemical or mechanical composition is not changed. So we will do cold welding, so it is not metal chemical or mechanical composition not changed. Clean joint is produced due to the no use of flux. This welding method is suitable for joining dissimilar metals. So this is also used for dissimilar metal joining. Limitations are difficult in remove of oxides and contaminated layer, long and time consuming process, surface should be parallel and well prepared. So these are some of the limitations. So we need to prepare the surface, right? The previous cases, right? Previous cases, ultrasonic welding, there is no surface preparation, but here we need to prepare the surface. So before welding, we need to make a surface. The applications of diffusion welding: fabrication of composite materials. This welding has large use in atomic reactor plants. So this is some of the applications for diffusion welding. So the next process is explosive welding. So SSW, solid state welding, is process in which rapid collisions of two metallic surface is caused by the energy of detonated explosive, right? So this is what explosive. So explosive means vedigundu padichi vedikira mari, right? So we have a object, so we will give explosive energy. That explosive energy is used to convert temperature rise. The temperature rise is used to make a joint. So no filler metal used, no external heat is applied, no diffusion occurs, time is too short. Bonding is metallurgical and combined with mechanical interlocking that results from a revolved or wavy interface between the metals. So these are some of the explosive welding. Applications are, this process has broad use in plugging of nuclear heat exchanger in chemical industries, suitable for joining of dissimilar metals. Right, so this is what explosive welding. We have an anvil and we have two objects and we have a detonator, right? This is like a anugundu, vedigundu mari, right? So if you give the supply, it will get explosive. That explosive energy is used to make a joint. This is what explosive welding. So it is illustrated picture shows that parent metal 2 is positioned above another parent metal which is to be welded, right? So we are planning to melt two metals, metal 1 and metal 2. Metal 1 placed on the top of the anvil and metal 2 is placed on the top of metal 1, right? So the explosive is placed on a buffer, right? So a piece of rubber or cupboard which protects the top surface of the damage. So explosive. So before placing explosive, we need to we use some protective device. The top of protective device, we place our explosive, right? So the parent metal placed on anvil, the detonator is ignited and exploded. Extremely high pressure is generated due to the explosion and provides a relative shear or sliding pressure between metal 2 and metal 1 or parent metal. A thin high velocity is formed on the surface of both metals due to the relative motion. This creates the sufficient velocity to stick the both metals, right? So sufficient to stick both metals. So this is what explosive welding. The next process is forge welding. It is the oldest welding process. We know that forging process, right? So we apply the force, and then we increase the temperature and we apply the force. We will make the forging. This is similar to here also. So forge welding is one of the melting process. It is the oldest welding process. It has an application of blacksmith method of metal joining. So assume that we have a two metal. We are planning to join these two. So we increase the temperature and we will give the hammering action. So these two metals should collide. So this is one of the forging, right? But only limitation is both the metals should be the same metal, similar metal, right? So the metals which is to be welded are heated in furnace or some other sources of heat to the plastic stage or just below the molten stage of metals. Then heated metals are brought on anvil from heat source. Apply the hammering or pressure together until a joint has been created. The application of heat must be uniform, otherwise the joint may be the weak or strongly rough appearance. So heat should not be too high or too little. To avoid oxidation, little amount of flux may be used in the welded joint. So right, this is what a forge welding. So it is similar to our forging process. We increase the temperature of base metal and we apply the pressure and we will make the joint, right? So these are some of the solid steel welding process. Now we are going to discuss with some newer welding. Why we say newer welding means it is a other process, right? So we are going to discuss two newer welding process. One is a laser beam welding, another one is a electron beam welding, right? So the laser beam welding means we are make a temperature with the help of laser beam, right, then we say it's a laser beam welding. If you are increase the temperature of base metal with the help of electron beam, then we say it's a electron beam welding, right. So electron beam requires vacuum, right. So in laser welding process, the heat is obtained from the application of concentrated coherent light beam, which is striking upon the weld metals, melts and metal, establish the weld joint. So this is very simple process. We are giving the high amount of laser at metal parts, two metal parts. So the laser will generate the temperature. That temperature it used to join these two metals. The heat is obtained from the application of concentrated coherent light beam called laser, which is striking upon the weld metal, melts the metal, establishes the weld joint. So this is the image of laser beam welding. So we have a one casting, I mean one housing part. Inside the housing we have a one tube, right. This is what xenon flash tube. This is like a xenon flash tube. The xenon flash tubes, the end of the xenon flash tube is connected with the mirror, right. So and we joined xenon flash tube with the laser crystals, right. So if you supply the electricity, the beams are generated. That beams are focused with the help of mirror, and it will pass on to the weld parts, laser beam. So this is what laser beam welding. We have a focusing lens to get a concentrated coherent light beam, right. So the ruby crystal is made of aluminum oxide with the chromium depressed throughout it. So the ruby crystals, this is a laser crystal. The ruby crystals are made of aluminum oxide with the chromium dispersed through it. Silver coated mirrors are fitted internally in the both sides. So we have a mirror, it is coated with the silver. The one side of mirror has tiny hole, right. It is a small hole through which the laser beam emerges, right. So one end of mirror has a fully closed mirror, and another one mirror we have a tiny holes, small holes. It is act as a passage for laser beam, right, leaving the laser beam, exit of laser beam. So a flash tube is placed around the ruby crystal, which is filled with the xenon insert gas. The flash is specially designed to operate on about 1000 flashes per second, right. So it will get the flashes. The electrical energy is converted to the light energy by flash tubes, right. So if you supply electrical energy, it will convert to the light energy. The capacitor is provided for storage of electrical energy, and it energizes the flash tube. As the ruby crystals are exposed to the intense light flashes, the chromium atoms of ruby crystals are excited and pumped into the high energy level, right. So at the end of the right, red light emitted by one atom hits another and hits further enhanced by the reflection of mirror to mirror, and again chromium atoms are excited, and finally the leaves through the tiny hole of crystal's mirrors. So this is what a crystal or coherent beam we can get. The narrow beam is focused by the optical focusing lens to produce a small intense of laser on the job. So advantages are materials which cannot be welded by ordinary welding process can be welded by laser welding process. Due to its high beam energy, both the welding and the cutting operations can be made effortlessly. So it is also used to cut also, laser cutting, right. So no electrode contaminations, narrow heat affected zones. These are some of the application advantages, but we have some limitations. It is a slow welding process. It is limited. We can use weld up to depth 1.5 mm. Materials such as magnesium tend to vaporize and produce surface wear. So we cannot use magnesium as a parent metal, right. So this is very simple process. So the thing is we have a mirror, right. So it is connected with the laser crystals, right. So and the xenon flash tube is covered in the laser crystals. If you supply the electrical energy converted to the high light energy. That light energy and the mirror is again coated with the chromium. Again it will get ignition state. So it will make a coherent beam. That coherent beam is exit at tiny holes present in the mirror, and it will focus with the help of focusing lens. So if you pass on the laser, it will create the temperature. The temperature you should make the joints. This is what laser beam welding. The applications are both welding and cutting is possible. High melting point and hard metals can be welded. Space and aircraft industries, disseminated metals can be joined. These are some of the applications. Right. So the final process is electron beam welding. So again, it is similar to laser beam, but only thing is instead of laser beam, here we are going to use electron beam. But electron beam requires vacuum, right? So it requires a vacuum. So it utilizes the energy from a fast moving beam of electrodes focused on the workpiece. Right, so this is similar to laser, right? The previous case we will generate laser with the help of ruby crystal and xenon flash tube. Here we are going to create electron beam with the help of some filaments, right? So we have a filament and we have a anode part as well as cathode part. The electrical energy is supplied to the filament and it will create the energy. That energy is passed on to the anode as well as cathode. So electron beam will generate. That electron beam is focused to the workpiece. And remember, it all the process is done in the vacuum chamber, right? So vacuum chamber, there is no air present, right? The filament of tungsten or titanium is heated to high temperature in a vacuum. So the filament metal is tungsten or tantalum. The electron is propelled from negative pole or cathode to positive pole or anode. The voltage is directly proportional to the electron velocity. Heat is directly proportional to electron velocity. So more electron velocity means more heat is obtained. The continuous strike of electron on the metal surface causes the kinetic energy, which has converted into the heat energy, which is sufficient to fuse the metal and join together. This is what the electron beam welding. So the advantages are a high quality of weld metal joint is produced. Different thickness of material can be welded easily. Much deeper weld joints is obtained in a single run. Seam and butt welds can be performed metals as a thin 25 micron level. Right, so we have some limitations. The cost of equipment is high because we need a vacuum chamber. It is more costlier. Time and equipment is required to create vacuum every time the job is made. Competent personnel is required. Workpiece size is restricted to the work chamber dimension. So these are the electron beam welding. The applications are it can give same performance TIG and plasma welding. This process is used in joining of reactor components. It has a large use in spaceship building. It uses automobile engine component welding, right? So these are the electron beam welding. Okay, right. So this is up to this we have discussed the solid state welding and newer weldings, right? So okay, thank you.